So now we've analyzed the first malware loader, let's have a look at the second one and see if the configuration is stored differently, see if we can figure out a way to extract it, and so on. So let's hop over to the virtual machine. So now we're going to go ahead and look at our second loader in this initial stages chapter. And for this second loader, I wanted to go for something more difficult and obfuscated, so I decided to go with Zloader. So the initial unpacking and everything involves it using PE injection to inject into msiexec.exe. So it will create a process and then inject into it. That typically takes quite a while, so I wanted to sort of skip that bit as we're going to cover injection later on. And I wanted to mainly focus on the loader elements. So when it does inject into msiexec, it doesn't call the DLL entry point or register server. It'll actually call a different function in the binary. And in this case, it wasn't actually recognized as a function by IDA, as it's never really referenced anywhere due to the amount of obfuscation that Zloader uses. And so it's basically calculated before create remote thread is called. And so what I've gone ahead and done here is, as I've analyzed this before, I went ahead and used Lumina to basically locate the config extraction part, and that allowed me to find the function here. But if you were going to do it yourself and you didn't have Lumina, you could pretty much detonate it in a debugger. Make sure you use run_dll32 to call the packed sample, follow it through execution, and make sure there's a breakpoint on create process internal W. At that point, you would then put a breakpoint on resume thread or create remote thread. And when that gets hit, you can see the offset. So you can then jump over to IDA and then start analyzing from that offset. So anyway, scrolling down, you can see there's quite a mess of functions and strings here. It also uses string encryption, which is also quite fun. But we're going to focus on the configuration extraction to begin with. So let's go ahead and jump over to the pseudocode because it makes it a hell of a lot easier to analyze. So this is the main function here called through msiexec. If we try and find cross-references, it can't be found. So having a quick look at the main function in pseudocode, we have this subroutine here that's called quite a lot, and it passes different values to it. So here we have this hex value, we've got another hex value here, and the first argument passed to it seems to differ. So here's 0, here's a 1, there's a 1 there and a 0. So at this point, I'm assuming there's API hashing going on in these functions based on the arguments passed, as well as the fact that with all this obfuscation, it would be pretty stupid not to put in API hashing. So let's rename this API hashing. If we step into this function here, we can see there's a lot more obfuscation going on. We then seem to recall API hashing again, so it will just call the same function if it doesn't get the correct API or something, or it will try and load another API here. So this could be load library or get procedure address. So here we have a function here, and this seems to be possibly a string decryption function. Here we have an XOR going on with this offset here, which points to this apparent string here. Okay, let's try convert that to a string. Is it a string or is that an actual byte? Press A. Okay, so this looks possibly like the string, not entirely sure, but that's for the string decryption, I'm guessing. So if we see what's passed into it, we see that this offset here plus A1. If you remember, A1 was the 0 and the 1 we saw being passed. So here we have 1 being passed and 0 here. So let's view what this offset is. So it points to a long list of unknown values. If we jump over here, we can see it seems to be some encrypted data. So what I'm guessing is this is probably going to be a list of DLLs that it's going to use to load. So for example, this could be kernel 32, this could be ntdll, and the value that is passed as argument 1 corresponds to the DLL. That saves having to locate the DLL in the process environment block and then hashing the different DLLs found to see if it matches and all that stuff. So I guess it's more efficient, although I don't know why they'd go for efficiency over security, because you can easily just figure out which DLL it's using. But anyway, moving on, let's actually name this function to string decrypt. Back out of here. So we can see here there's actually a few string decrypts called, but let's jump into the first function here because I think we've pretty much figured out as much as we can at the moment. So let's step into the first function. We have this subroutine here, we've got a string decrypt, this subroutine here, another subroutine here, we've got several more subroutines. This one contains a unknown value and then what seems to be a string. Okay, so there's an interesting string there that's been recognized by IDA, and it's all lowercase characters as well. It's not random bytes like this stuff here. So this could be a decryption string or a cipher or something inside there, so we'll have to look at that later. So there's this subroutine and a few more, and none of these have arguments it seems, but I have a feeling if we jump into these, jump back out, okay. Sometimes because of the amount of obfuscation, IDA doesn't do a very good job of passing everything the first time. You've got to sort of jump into them and then refresh to see if it'll recognize any arguments. Okay, doesn't look like it. Oh, there we go, we just resolved something there. Looks like the type of the function. Step into there, step out, okay. And so we have a call to a string decrypt function here. Let's step into here. Okay, it's got this fairly small string here. It's nothing too big, not entirely sure what it is because we haven't got a string decryptor. So we could go through each function we see here, so go into here and then go into here and then continue. But because of the amount of obfuscation, like if we jump into this one, we can see all of the operations performed just to perform an OR operation with argument 1 and 2. It would take quite a while if we were going through it manually, and because we don't have any scripts to deobfuscate everything for us, we'll have to try and be as efficient as possible. So because to begin with we're looking for a configuration, I'm looking at these two values here, and it's quite odd that you're going to see a string that's about 20 bytes in length, all the same format, so lowercase characters. So I think there's something important going on here. So if we step into this function here, we can see there's quite a few more functions. It seems to assign some D words. So V7 gets assigned to these D words here. So V7 gets assigned to this, V6 to that, V8 to that, and V9 to that. So if you remember iced-id, it had variables inside of the configuration. So I believe it was that 4 bytes that was assigned to the string sent to the command and control server. In this case, I have a feeling it's going to be doing the same because we can see V6 is being used in these two subroutines here, and then it's moved into a D word. And if we check for cross references, so we can see it's being used in this other subroutine. So if we jump to it, we can see that it's being returned. Find cross references to this. So V12 will contain our D word, which could be from the configuration. Now, if you've ever looked at the Zeus banking Trojan, you will probably recognize a value like this and the whole bin storage and everything. So we'll look into the communications once we've got an idea of how the config is stored, but basically this takes a lot of code from the source code of the Zeus banking Trojan that was leaked a while ago. So let's jump back to the possible config decryption function and let's have a look at what these functions do. So we step into this first one here. We have this D word XORed with this value here, which is returned to V2. Step into this one. It's just a wrapper function. Step into this one again. We call subroutine here. All this obfuscation is really not fun, but it will return V3, which is going to be 777, or it's going to be 0. So as you can see, this function here is entirely useless, and all that it's doing is comparing A1 to A2, and it will return a value based on that. So A1 is passed in through that, and A2 is a 0. So we then have this API hashing call, which will be moved into V3, and V3 will be called. So it will load an API and then call it. And then if we jump into this subroutine here, we can see it returns V3, which is another D word XORed with this value. So that's not important really. So now let's jump into this function. Okay, that will just return this. So let's rename that because it's used twice. So ret this, and we've got this D word. And then we have V3 being assigned to this D word. Is this used anywhere? It is pushed to a function, it seems. So then we have this subroutine called here, which returns another value, which is calculated through XORing a D word and this value here. So if we actually view the D words, you can see there's a lot of stuff here, and this is all used for calculation of offsets or calculation of values that need to be used. So you could go ahead and probably write a script to automatically calculate all of these for you. So find the cross references. So find the cross reference, go to it, and then figure out what it's being used. So you can see it's being XORed here. You could rename the D word to whatever value is returned. But obviously that's a bit more in depth for what we're doing here. So that's stored in v4. If we step into this value, we can see that it will loop through something based on A3, which is probably going to be a length because it loops until I equals A3, and I is incremented on each loop. So I'm going to guess A3 is a counter. So let's rename that to counter. And so as it loops through, it will do A1 plus I is equal to A2 plus I. So that looks like it's copying a byte from A2 plus the counter into A1 plus the counter. So in that case, I'm going to say A1 is the destination and A2 is the source. So this is basically an implementation of what seems to be memcopy. If we jump into this, it just returns A2 plus A1, which seems to be possibly returning a length. So what I'm going to do is name this Zloader memcopy, because that's what it basically does. So it will copy A1 into V3. A1 is that unknown region of memory. So if we refresh that and rename this to new A1. So new A1 doesn't seem to be used anywhere, although it is stored inside of this D word here. I'm not sure if that's going to be used as a pointer to the decrypted configuration, if it is that. So anyway, we can see A1 is copied into new A1, and then we have this subroutine here. If we jump into here, we have a check to see if A3 is equal to -1, and if it is, then it will call this subroutine here, where it performs a check on A1, sets the result as -1, and then it will loop around, seemingly incrementing result. So it'll return the result and store it in V3. So V3 could be a length in this point, and it is used in a memcopy function again, so most likely going to be a length. We can see A2 is copied into A1. So this is probably I'd say a wrapper for the memcopy function. So I've named this Zloader memcopy unknown size. So because it will basically calculate a size with this function here. So let's rename this memcopy unknown size. So this will copy A2 to this unknown value here. And A2 is that interesting string we saw. So let's rename this to interesting string. And then we return V6, which doesn't seem to be used for anything. So what I'm going to do is I'm going to press F5 again to reanalyze this code and see if anything changes. Okay, it didn't. So obviously the return value doesn't seem to be very useful. So let's jump into this function. So here we have another call to Zloader memcopy, where I'll copy this D word here, which is 0, into this. And V1 is assigned to this, which is used down here. So then we have this function here, which will basically get the size again. So this will get the size of the interesting string. So let's rename V2 to size of interesting string. Interesting string is passed in as the first value. This looks to be a size, so 751. And then V1 contains this D word here. So let's rename to contains D word. Now let's find cross references to this. And as you can see, it'll contain ESI, which is moved into it. If we jump to it, it's actually this D word we saw in the previous function. So new A1 contains our first unknown value that was passed in. So if we jump back to the calling function, we can see this is going to be A1. So let's rename A1 to possible config. So possible config is moved into new A1, and then here we can see that a pointer to new A1 was stored in this D word. So let's rename this to pointer to config. And now let's jump back into this function here. So now we can see that we have this subroutine called, which takes the interesting string, the size of the interesting string, the pointer to the config. Let's rename this to pointer to config. So this is pointing to this which points to the pointer to the config, and it's all confusing. But basically, this function takes the interesting string, the size of the interesting string, the possible config, and the size, I'm guessing, of the configuration. So now we know what arguments are pushed to this function. Let's step into it. So we have this first subroutine and this second one. Let's step into the first one. And immediately upon doing so, I notice the value 256 appear twice, and what seems to be a while loop that will compare v4 with result. Result is equal to the return value of this here, which is another mess, A1 XORed with A2. So this will be the same result each time because A1 and A2 don't change. But rather than figure that out, we can probably make some assumptions based on what we see in the rest of the function. So looking at the very top of the function, V3 is set to 0. A3 plus 256 is set to 0. Then we enter our first loop, which will do A3 plus V3 equals V3, and then increment V3. So on every loop, it basically goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. And this will continue until the value returned from this function is not 0. So if we jump into this, it will return V11. V11 equals V7. V7 equals 233 unless A1 doesn't equal A2, in which case it will return 0. If A1 is equal to A2, then it will return 233, making this break out of the loop. So that means V3 must equal 256. So this is making what I believe is going to be a substitution box for RC4 encryption. And therefore the scrambling of this RC4 substitution box is probably going to be done in this loop here. So I would guess that the return value of this function is going to be 256. There's no actual decryption going on here, so we can simply name this RC4 init for RC4 initialize, and then we step into this subroutine here, and this is where the RC4 decryption is going on. So here we can see there's an XOR with the value returned from this, which is A1 in an OR operation with A2, and yeah, pretty much all it does here, even though it looks like there's a lot more going on, that's just because of the obfuscation inside of Zloader. It's basically an RC4 decryption operation. Here you can see A1 plus V6, so V6 is going to be the counter, and we've got V11 here. So V11 is A1 plus V6, and in that case what it will do is for every loop it will overwrite the encrypted data. So rather than allocate a new region of memory and then have V11 XORed with V12 copied into V10, it will simply overwrite the encrypted data. So A1 plus V6 is equal to 1 byte. So V11 is equal to A1 plus A6. And the return value of this is equal to A3 plus V10. V10 is equal to V9, and the return value of this subroutine, V9 is equal to V8, and V8 is equal to A3 plus V7. V7 is equal to V4 plus V6. And it's basically just a lot of obfuscation trying to slow research down and, to figure out that this is in fact an RC4 decryption loop, as well as to prevent Yara rules triggering when it sees this. At this point, we're pretty confident that it's using RC4 encryption. So let's name this to RC4 crypt. We can back out and change this to RC4 crypt. Back out again, change this to decrypt config because that's what it is doing, and then we can back out once again. So we have our configuration here. Let's select all of the data here. So let's scroll all the way down until we get to that 20 byte character string. Here we are, and we want to select all of that and then Shift E. So now we can extract it as hex data. And what we're going to want to do is we're going to jump over to a CyberChef instance. And we're going to see if we can decrypt this without any other knowledge on whether it uses RC4 or not. So let's copy that out, jump over to our CyberChef instance, paste it in here. Then we want to do from hex, put that in there, and select RC4. Now we're going to jump back to the IDA instance and copy out this 20 byte key. Jump back over to CyberChef and paste this in. So immediately you can see that we now have URLs. We've got this string down here, which could be an MD5 hash, could be an encryption key, And there's a few other values here. So we've got 2503 here. We've got a JHO. I'm not sure what this data is supposed to be. So now we've figured out how the configuration is stored, we can go ahead and perform a brief analysis on the communications routine before moving over to automated config extractor development. So let's go ahead and jump back over to IDA. Okay, so now we're going to go ahead and have a brief look at the communications routine. So when we were looking at this config extraction, we had this D word here being used in a possible communications function. So if we find the cross references, jump to the cross reference and do the same for this function, we end up in this what seems to be a packet routine. And the reason I think this is mainly because of the values that seem to be passed into this one function here. So what I was saying before is the Zloader dropper and the follow-up malware takes a lot of inspiration from the Zeus banking Trojan, as well as borrowing a lot of code from the leaked source. So if you remember, when we look at algorithms and all those sorts of stuff, the first thing we normally look for is constants. And in this case, we have values that look like they're specifically meant to be there. So they're not random values because they all have this 1, 0, 0 and then the numbers after it. So at this point, what I would go ahead and do is I would search up this value, which I have actually gone and done. So let's go ahead and jump over to Chrome quickly. So I've searched up Zeus and then 10002, which is the value that we can see over here. And then I added communication on the end. So the first thing that comes up is some company called Zeus Communications. And the second thing that comes up is this PDF file on honeynet.it. And we can see that when item 1002 is specified by the botmaster, we've got item 1003. So let's click that and Control F. 10002. We have a whole list of item IDs here. So 1002 is the botnet ID. Then we have the bot version, the bot ID, net latency. We have all these values used in the communications here. As you can see, it mentions TCP packets and command and control servers. So at this point, I'm guessing this function is related to the communications routine. Let's jump into this routine here. We've got quite a bit of obfuscation. Let's go ahead and actually name the arguments passed to it. So the first argument in our case is unknown. The second argument is the ID. So let's rename A2 to ID. Argument 3 is equal to a possible flag or something. So let's rename that to possible flag. A4 is equal to V12, which is returned from this function, which returns the value from the config. So I'm guessing V12 is going to be our data here. So rename that to data. And then A5 is going to be probably the length. So here we see 4 is passed in. As we scroll down, 4 is passed in there. This one looks like another function related to the packet structure, as it has the same values passed, but this time no size. So that could be a string there, and it basically works out the size inside of the function. But anyway, let's jump back into here, rename this to size. And because there's nothing really verbose about what A1 is, we'll have to pretty much figure that out inside of this function. So there's not really much verbose about A1 here. It's passed in through this function here. So if we go and find cross references, we see the call here. A1 is V6. V6 is set to 0. Not really very helpful. Here, A1 is passed in as an argument again. V14. V14 is in here. Okay, anything really useful? Step into these functions. Looks like it's doing some more API hashing. So because there's no other explanation for what these functions could be, I'm going to go ahead and say A1 is equal to empty memory. And the reason for this is because the data has to be stored somewhere, and it seems that A1 is being used quite a lot, so it's moved into V9. V9 is used in a memcopy function here, so data is copied to V9 plus V16 plus the value 16. So I'm going to assume that this is going to be empty memory, which will contain our packet. So we can see V5 here, it will get the data inside of empty memory at position 20. It will then perform this, which will add A1 and A2. If we try and see what these values are, it will basically add these hex values together from the looks of it. and it will return that to v6. So as we scroll down, we have this subroutine here. Inside this subroutine, we have a few more subroutines. We've got some API hashing going on here, some more obfuscated functions, more API hashing. Then we have the obviously empty memory moved into v9. v9 contains the empty memory, and that is eventually filled with the data passed in as the function and the size. We then go ahead and call this function here, which XORs this D word with this value. v14 is equal to v17 plus 20 plus v12 minus this subroutine here, which is a1 minus a2. a1 is 0, v13 is equal to the return value of this function. So performing basic static analysis isn't the easiest, especially in the case of Zloader. A lot of it is sort of guesswork, although because we do have the knowledge that it is in fact using, code from Zeus, or at least IDs from it, let's jump back over to Chrome. And what we can go ahead and do is simply search for the Zeus source code, because it was leaked quite a while ago. And hopefully we can find some sort of interesting information from it. Maybe they've stolen this particular function from it, or they've put a spin on it and it's somewhat similar, or it could be completely different, but there's no harm in searching for it. So searching that in, we can see that the first post isn't what we want, and the second post is a GitHub repository of the Zeus Trojan horse, leaked in 2011. So we know what values we're looking for, so we have to deal with the value 10029. So let's see if we can search it in this GitHub repository, and we might be able to locate the packet generation routine. So 10029, we can't seem to locate anything, but then again, in the PDF document, we didn't actually see 10029 being used. We saw 10002 being used. So let's replace this with another 0 and a 2. And here we can see that in source common config.h, we have this sbcid botnet being used. So if you remember back on the PDF, we saw these values being mentioned. So let's go ahead and select this. And we don't really want to look through the config, but we can go ahead and copy this out, paste it in, and search for this value. So we've got config, defines, gate, some global stuff, and then we have this report C++ code. So stepping into this, Control F again, and paste in the sbcid botnet. We have this being passed into a function called add item as UTF-8 string, and this is actually linked to the bin storage. So at this point, this is quite interesting. Let's go ahead and copy this out. And we want to go ahead and find the bin storage source code. So let's search for it. We've got report, bin storage.h, and bin storage.cpp. So we've got this pack function here, which is a structure. So we've got dword size, byte flags, storage array header. We have a check hash function, create empty, and then we have this add item function. Although it's not the add item as UTF string, it is close to what we're looking for. So as we scroll down, you may be able to see similarities to the function we have over here. Let's just go ahead and scroll down a bit. So even though it is obfuscated a bit, we can sort of see similarities between the code. So here we have new storage size equals bin storage, and then size plus size of item plus data size. This is basically what this function here does. It will move the size of the bin storage from the looks of it into v5, and then it will calculate size plus this value plus that value. Then it will go ahead and add v5 and v6 together, therefore adding the size of the bin storage with the size of the item, so passed in as an argument. We then have this storage p is equal to bin storage, so it's just a pointer. We have exactly the same thing here, v9 equals empty memory, and then here we have this item variable, which is equal to p plus the size of the bin storage, and you can see here v16 is equal to the size of the bin storage, then v10 is equal to the empty memory, which in this case is equal to p, so this is basically a pointer to the bin storage, plus v16, which is the size. So we have the item variable, which is v10, we have the P variable, which is v9. Scrolling down, it seems to checks to see if the flags variable is equal to item f compressed. This is most likely what this if v7 and 1 is equal to. And in this source code, it will seemingly compress the data. It doesn't seem to have that in here. So moving on, it will check if it isn't equal to compressed, and in which case it will go ahead and copy the data from data to dest, and that's what this memcopy here is. So scrolling down, we can see some more similarities. So we've got full item size is equal to size of item plus item dash size. And then we have this new storage size is equal to the bin storage size plus the full item size. And it checks to see if it's less than or equal to the max size. And then what it will go ahead and do is it will move ID into bin storage dash ID, and then flags into bin storage dash flags. And then the data size is moved into the bin storage dash real size, which is exactly what's going on down here. It's just IDA hasn't recognized it as a structure. So here we have v11 is equal to ID. We can see that is what occurs here. v11.1 is equal to v7, which is going to be linked to the flag, as you can see here. Then we have the real size, which is v11.3 and then equals size, and then it will increment v17 plus 28. So that pretty much shows you how you can go ahead and find a constant inside of a open source malware family. So if it's called Zloader and has links to Zeus, there's probably a high chance that it will have some form of constant inside of it that will be linked to the original Zeus code. So when it comes to emulating this malware family, we're not going to be writing an emulator, although I will be showing you a few tricks to make it a lot easier to write an emulator for. So we'll be looking at how to turn these v11.1s into structs. So we'll actually be a bin storage structure, as well as turning these values into our own strings. So rather than having 10029, we can set it as SBCID botnet. So that just makes analysis a bit faster, and we'll also have a look at what these flags actually mean. So now we know a bit about how the packet structure looks and the internals of it, we can go ahead and write a config extractor to extract the configuration from this sample. And then we'll go ahead and have a look at how we can make analysis easier. So let's go ahead and jump over to writing some Python. Okay, so to recap, in this part of the chapter, we looked at the second stage loaders and my personal method of analyzing them while developing a configuration extractor and a communications emulator. We also had a look at two different malware loaders and reverse engineered them to find out how the configuration is stored. So in the next part of this chapter, we're going to be looking at automating analysis. So using the information we gathered from reverse engineering the previous two loaders, we're going to be developing our config extractor for them, as well as a communications emulator. And so that brings an end to this part of the chapter. So thanks for watching, and I'll see you in the next part.